All right, let's get started. Hello, everyone. My name is Justin Taft, and I'm a security consultant at NCC Group. Today, I'm proud to present some research I've done on GPU security. We're going to focus on exploiting shared memory through the Adreno GPU. This vulnerability actually affected multiple devices such as the Nexus 5X and 6. So there's going to be some pretty cool stuff in this presentation. As a quick overview, we're going to discuss shared memory internals. We're going to see how shared memory is actually configured and set up and dive a bit into the hardware. Then we're going to discuss what the GPU command processor is and see how it plays a role in exploiting this vulnerability. And finally, we'll actually dig into the details about the vulnerability, and I'll do a live demonstration at the end, showing how we could gain root access. So shared memory, what is it? If you talk to your software engineer, they're going to tell you it's a region of physical memory shared between two or more processes. A common example of this is dynamic libraries. So instead of loading a dynamic library multiple times into memory, you load it once and you share the memory between multiple processes. This cuts down on memory usage for the computer. Additionally, shared memory is used for inter-process communication. So when you have two processes that want to communicate with each other, you could map the same memory page into both processes and read and write values. So this is very quick and has low overhead. If you ask a hardware engineer what's shared memory, you're going to get a little different response. So it's a region of physical memory shared between two or more hardware components. In our case, we're going to be discussing the GPU and CPU sharing memory through system memory, aka RAM. And generally, this is used to transfer information back and forth between devices, such as textures for video graphics. So as a quick overview of the hardware involved with shared memory, there's a couple of missing pieces here, but this is basically what we need to cover for the actual vulnerability. And basically, the important thing to take away from these slides are these two devices called the MMU and IOMMU. These translate virtual addresses or device addresses to the physical address where the actually memory lies in system RAM. And basically, the bug will exploits this exploits the setup. So let's discuss a little bit more about the MMUs and what they are. So MMU stands for Memory Management Unit. It's a hardware component that CPU interacts with when accessing memory. Usually this is within the same die as the CPU. Before it was an external component, but not anymore. Again, its main role is to translate virtual addresses to physical addresses. So for example, if you have a process and you try to access an area of memory that's not mapped to it, this MMU will signal to the CPU that it was an invalid operation, and then the kernel can decide what to do, such as raising a segfault signal to the process. Additionally, the MMU enforces page table entry flags, such as rewrite and execute. So again, if you try to write to a read-only page, then the MMU will signal the CPU saying this can't happen, and the kernel can decide what to do, such as raising a exe bad access signal to the process. So the main thing to take away from this slide is that the MMUs are used to enforce security. They basically sandbox processes from one another, so they can't write to arbitrary memory regions. So now we'll discuss what the IO MMU is. It's called the Input-Output Memory Management Unit, and it's very similar to the MMU. So basically, the IO MMU is a hardware component the GPU interacts with when accessing memory, and it can be configured to map an address range to system memory, which can be used by the CPU. Please note that the term IO MMU is not something specific to the GPU. There could be multiple IO MMUs on a motherboard, for instance. But in this case, we're discussing the GPU's IO MMU. And basically, what the IO MMU is responsible for is preventing direct memory attacks by limiting what memory the actual hardware could interact with. So cool, that's basically what shared memory is. How do we actually set up shared memory with the GPU, with the Adreno GPU? First thing we have to discuss is interfacing with the graphics driver. And this is actually pretty simple. So the Adreno graphics driver exposes a device file /dev/kgsl3d0. And basically, you interact with this device file by sending IO control commands. This file has global read and write permissions, so pretty much any process on the phone can talk to it. You might run into some issues where there's SE Linux that prevents certain processes from interacting. But again, if SE Linux is enabled, then pretty much anyone can interact with this file. So here's an example IO control command that we could use to map shared memory. And just making sure, can everyone see that in the back? Awesome, thank you. So it's a simple structure that we send to the IO control command. We have a host pointer here, which points to the CPU virtual address that we want to share. Again, we're sharing pages of memory for 4,096 bytes. And this host pointer must be page aligned. The next thing we specify is how many pages or how many bytes you want to share. And this has to be a multiple of the page size. Then there's the tribute men type, which specifies what type of mapping we want to create. In this instance, we tone the driver that we want to map some memory that's already owned by the process into the GPU memory address. And finally, we have the GPU address attribute. And this gets updated by the IO control call when it successfully succeeds. And this will point to the GPU's actual device address where the mapping is. There's a bunch of other different maps you could do. There's one called IM buffer where you could carve out a huge chunk of memory that's contiguous. And yeah, if you browse basically the source code of the kernel for this driver, you could see all this, see all the different types. Cool. So that was shared memory. It's pretty straightforward. Let's talk about the GPU command processor and what it is. So the GPU command processor processes instructions in order to draw graphics and configure internal settings of the GPU. And higher level APIs such as OpenGL provide an abstraction for implementation details. So generally, OpenGL has something called a user mode driver, and it basically contains a bunch of vendor specific code in order to generate these instructions for the command processor. So whenever you say like draw like a rectangle on the screen, the user mode driver will go ahead and create a bunch of these instructions to the for the GPU and then send them off to the driver to actually process. So as you can guess, these command processor instructions are not standardized. GPU manufacturers can decide whatever types of instructions they want to provide. They can make. They just have to like follow the OpenGL like specification or whatever graphics API that they want to be compatible with. And one thing to note is that through the GPU command processor, the Arduino's MMU is actually configured on boot up through the command processor. It generates a bunch of commands to do this. So let's go ahead and take a look at how we could write to GPU memory from the command processor. And again, this is done through the command processor. All we have to do is allocate a buffer, and then we send that buffer to the graphics driver. So here, the Arduino GPU actually provides a simple command called cpmemrite, which allows us to pass two more arguments, which is a target GPU address we want to write to and a value that we want to write. So this is pretty straightforward. Later on, when it's actually time to send the commands, there's a bunch of ceremony that has to go on. You have to create some structure defining how many instructions you want to send and where the instructions lie in GPU memory. So normally these command processor commands you have to map into the GPU first. And you also have something called drawing context, which you associate all these command processor instructions with. I won't go into all the details here, but basically it's just another simple IO control command used to actually submit the commands. And one thing to note is that these commands actually execute in parallel. So yeah, it's kind of like a fire and forget scenario, but there's actually a couple of command processor commands you could get notified when actually finished processing them. Cool. Well, let's talk about the vulnerability now. So we talked about shared memory, how to set that up. We talked about how we could actually write from the command processor into GPU memory. What's the actual vulnerability? Because as I discussed, we're attacking shared memory, and when you try to write to read-only memory, normally that can't happen, like the MMU prevents it. Well, it turns out I actually got a CVE for this, is that the Arduino graphics driver maps memory pages marked as read-only by the CPU as writable by the GPU. So this is huge. This has a lot of repercussions. And I'll go into more details about the vulnerability. So here's basically a permission check that occurs while you're trying to map memory into the GPU. It's pretty straightforward. The main thing to focus on is this get user pages function call. What this does is it's used to pin memory in place for direct memory access operations. So you want to pin memory in place for direct memory access because you don't want that page to be moving around while you're trying to read or write to it, because you could be, who knows what you'd be reading or writing to. Additionally, this function has some internal code to verify the flag you pass in if you're reading or writing that actually matches what the underlying page flags have. So basically, if you're trying to ask to write to a read-only memory page, this function would normally fail. However, if you take a look at the line above where it says int write equals, this flag actually gets inverted. So when we request to map some memory as read-only, this check is bypassed because it gets marked as, or sorry, when we ask to pin this as write-only, this flag is inverted as read, and it gets, the check passes since the actual page is readable. So this is how we could basically say we're going to write to a read-only memory page. Again, this actual get user pages function only pins memory in place. This isn't configuring the IO MMU. Later on, the IO MMU configuration actually happens for the GPU. So this is where the initial memory or the initial request where we say we want to write to the map this memory as writable into the GPU occurs, and basically the mapping continues and it gets mapped as writable. So again, to sum up what I just explained, this allows us to map read-only memory pages into the GPU. So, okay, now that's out of the way, let's talk about the exploit. What can they actually do because of this? The very first idea I had was modify dynamic libraries, right? So when you have a dynamic library, typically they're shared between multiple processes. So you could, for instance, in a process, you could use the functions dl-open and dl-ysym to load a dynamic library and locate the symbol addresses. Then after that, you could go ahead and, using the command processor, overwrite the arbitrary functions such as Android log print and liblog.so. So again, when you change it in one process, since that memory is shared between multiple processes, all the others will start executing those new instructions. So this is pretty cool. Additionally, the other reason I targeted the Android log print symbol is because this is generally just for logging, and it doesn't have a return value, and it's not going to have any nasty side effects if you overwrite it, so it's pretty safe too. The one downside with this actual attack when modifying dynamic libraries is that some privileged binaries are statically linked, so you can't modify dynamic libraries in order to influence the operation of statically linked libraries. But we can do a bit better. If we actually think about how shared libraries work, it's just an mmap underneath the hood, and mmap just acts as a disk cache. So whenever you load a file into memory through mmap, the contents are shared between multiple processes as long as nobody writes to it. So we could actually go ahead and modify the disk cache directly. We could mmap any file that we have read access to right into memory. So when any other, so when we mmap it, contents of the file are cached in memory for other processes to use. So we could exploit this by mmapping a SUID binary into memory, and then we could overwrite the instructions of the SUID binary to insert our own program in memory. So this is awesome because this allows us to effectively replace one SUID binary that we could just read with and just put whatever instructions we want into it. Last thing to note is that changes aren't actually stored to disk. They're only cached in memory. So once the device reboots, the changes are gone. But yeah, that's basically the vulnerability. And I'm going to do something a little bit risky here. I'm going to try a live demonstration. I'm still tweaking this exploit to make it work all the time. It pretty much works like 5 out of 7 times. Then I have to reboot the phone in case it doesn't. There might be some fancy copy and write stuff going on under the hood, but yeah, let's see if it works first go. If it doesn't, I have it recorded, so no worries. Let me see if I could put this on the right screen first. What did I do here? 1 second, sorry. Okay. This is going to be a little weird because I had presenter mode on my screen, so I have to tilt my head here. So let me fire up the phone. Okay, should be booting. Go ahead and wait a second for this to connect. Oh, actually, there's another screen here. Yeah, thank you. I think that was the right device. Just verify. Yeah. Cool. So let me wait for this to finish booting. Go full screen. Cool. Awesome. Okay, so the phone just booted. Let me log into the phone. Okay, so here we're just doing a normal ADB, nothing crazy. If you run the run as command, it's a standard output that you see of the actual program. And if we type ID, you see our user ID is set to 2000, our group ID is also set to 2000. So this is just our normal permissions. So let me go ahead and go to our directory where the actual exploit is. And what you saw on the slide was pretty much the essence of the exploit. This is just a low glorified version. So here I can specify input file that I want to read instructions from. So here I'm going to read my program called root shell, which just simply calls set user ID to 0 and it executes a shell. Then as the output file, I'm going to target the system bin/run as binary. Okay, let's see if this actually goes. Oh, let me show this really quick. All right, I think I just ran into Murphy's Law here. Yeah, let me jump to the pre-recorded demonstration. I could show you after the talk in person if you'd like to see it running. Like I said, there's some fancy copy on write stuff going on underneath the hood, I believe. But let me pull this over here. Oops. Sorry about this. Give me 1 second. Boom. So yeah, this is the same thing, just a recording of a session I did last night. So as you just saw, we call it run as. Jump a little bit forward. And yeah, just let it play. So again, here I'm specifying the actual command to run, which will go ahead and overwrite the binary. And then the actual exploit starts running. Should in a second. There we go. So there you go. You see the actual binary is starting to copy over. And one thing that's interesting about this exploit is that while it's actually running, if I start playing around with the phone, the quicker the progress moves. I think this is because the instructions for the command processor actually get forced to flush because stuff has to render to the screen. So while it's uploading, I'm writing about 160 bytes per second. Then I'm sleeping for about 100 milliseconds and just verifying it actually persisted in memory, just so the contents are there. So this will just take another minute. Yeah, and in case you're curious, the way you could discover additional command processor commands, you could either find like open source driver, or a lot of these are actually undocumented. So you could like hook OpenGL, for instance, and try to figure out where they're constructing these instructions and issue them yourself. So as you saw, the actual exploit just finished running. Then when the run as command executes, our target program runs, which simply runs our set user ID to 0 and changes the SE Linux context to untrusted app. And there you can see the user ID is 0 and the group ID is also 0. So yeah, that's basically the vulnerability. Through the GPU, we're able to get some privilege escalation. Oh, thank you. Thank you so much. So let me get the slide back, the presentation back on the screen really quick. Give you 1 second. There's that. There's that. Cool. So again, so what the takeaways of this talk? This was actually a shorter talk, 25 minutes that I submitted. But yeah, here's the takeaways. Shared memory is hard to get right. If you have multiple hardware components accessing the same physical region, you have to make sure like the security like for accessing this page is synced across all devices. For example, you probably don't want one device that's only reading a memory page and have another device that's writing it. In this case, this is what occurred. Direct memory attacks are very powerful. So some direct memory attacks actually allow you to write to any physical memory range. In this case, it was a bit limited. We only could write to the range with our own process, but again, it actually affected other processes because of the disk cache. And the other thing to know about this is that like mitigation such as ASLR didn't come into play at all, which is a very nice like side, which is very nice to have. And last thing to know is that graphics security has a very large attack surface. What I just showed here is like the tip of the iceberg. There's stuff like buggy shader compilers to video graphics not being cleared from memory. And yeah, I definitely going to be going to do further research into this area. So if you're interested in this stuff, I really recommend you check out our blog at NCC Group. Go to nccgroup.trust. We publish our research there. We actually have a Twitter account, NCC Group InfoSec, I believe. And we let people know about upcoming talks and additional research. And yeah, so again, thanks for everyone for coming. This is my first Black Hat talk, and I really appreciate the support. So are there any questions about anything? Cool, that's easy. Awesome. Well, I hope everyone had an awesome experience at Black Hat. I hope I can present again in the future and look forward to seeing everyone again. Cool.